Good evening, everyone, and welcome to the Royal Observatory Greenwich's live stream of observing Mars. Now, our live stream might look a little different today because you can see that I'm not actually in a telescope dome, and that is due to social distancing. But we are using our telescope and we will be delivering our Mars feed to you. However, due to social distancing, I cannot be in the dome at the same time as our other astronomers using the telescope. So Dr. Greg Brown, who you'll have seen just in that short time lapse at the beginning there, is operating the telescope dome this evening along with our astronomer Bryony Langan. So shout out to them for helping us. Now, hopefully you're joining us through either Facebook Live, YouTube or Zoom as well as part of the Royal Astronomical Society's National Astronomy Week. And so you can interact with us if you've got any questions throughout the stream, then whichever service you're tuning in from, just send in your questions. At the end of this stream, I'll answer as many as I can, but send them in along the way, and if I can answer them as we go along, then I will. My name is Hannah Banyard. I'm one of the astronomers at the Royal Observatory, and I will be your host for today, so you'll be hearing mostly from me. Now, I mentioned that I'm not in the telescope dome that we're using, but I am technically in a telescope dome. So I'm at the observatory in the south building in the Endeavour Room, and above me is a beautiful dome known as the Lassell Dome, which was built in 1884 to house the Lassell telescope, and it was on ground level, but then it was actually raised up to its current position now. If you've ever been to the observatory, it's the dome further back that you can see up nice and high now, and it was moved up to house two much larger telescopes, a 26-inch refractor and a 30-inch reflector. For a few years it was actually a planetarium too, but now it is our lovely library and stores some beautiful artifacts too. So coming up in our stream, we'll of course be having a look at the live views through our telescope. We want as many of you to observe Mars as possible. And as well, we've got an interview with Greg to talk to you about the telescope that we're using this evening, our Annie Maunder Astrographic Telescope. We've also got an interview with Professor Sanjeev Gupta from the Imperial College London, who's going to tell us a little bit about the missions that he's worked on that are on Mars right now. So we'll be dropping in and out from the live stream. Hopefully we'll be able to see something this evening, but we are of course in the UK, and here in London the weather on my way in was quite cloudy. We are hoping for some breaks in the cloud, but I think we'll head straight over to the live stream and see if we can see anything. And unfortunately, absolutely not at the moment. We'll keep an eye on the sky, but this is one of the biggest problems with astronomy is of course our weather, especially in a city like London when we have things like flight paths as well. And this can just affect the weather and make it quite difficult for us to observe the objects that we want to look at. But luckily, because Mars is so bright, we will be able to see it even if we've got some thin clouds. So we don't need crystal clear skies this evening, we just need a little break in the cloud. Now, thankfully, we were able to get some footage of Mars last week so that you can see what we should be seeing through our telescope right about now. Now, some of you might be a little bit underwhelmed at the view currently, which is understandable because when you think of Mars, you think of that bright orange-red light in the sky. Now, we're using a black and white camera, so we can only get black and white light here. So we can't see Mars in its glory of all that beautiful red-orange colour. But importantly, you can still see some features here. So you should notice there's a big difference between the top and the bottom of the image. And this is due to the Martian dichotomy, where the north half of Mars is much smoother and lower than the rougher, higher south. Now, this image, video even is actually flipped. So south is at the bottom, south is at the top, and north is at the bottom. And that's due to when we view things through reflector telescopes, the image gets inverted. So don't worry about that. So what you're looking at now, the top, that darker region, that's the south. And so it's a lot bumpier. And we get this, it looks darker from the reflected light from all of those bumpy features. Now, the south is also home to many different craters, which give us an idea of age. So the more craters an area has, the older it is because it hasn't been resurfaced by, say, tectonic activity, where lava can fill in old craters and smooth out an area. Now, we're not quite sure why there is this dichotomy between the two hemispheres of Mars. There is some suggestion that perhaps a moon-sized object crashed into Mars at some point at sort of an angle and caused the smoothing on the north half of Mars there. But it's something that we're not so sure about. And this is why we should still keep investigating Mars more closely. But let's talk about Mars as a planet itself first. So Mars is the fourth planet from the Sun. It's the last of the inner terrestrial planets. So that's somewhat Earth-like. A terrestrial planet is a bit like Earth, as in it's rocky. So we can stand on it. It's more of a normal planet we're used to than, say, the giant planets like Jupiter and Saturn. And Mars does look red from Earth, so I hope you have been outside over the last few months and seen it up in the sky. Here in London, I've heard a lot of people say it looks like a red light on the end of a crane because it's so bright, it looks like an LED. But it gets this colour from its surface. So the dusty surface is an orangey red colour because it's covered in iron oxide. So it's essentially just rusty, and that's why it does look reddish orange just to your eyes. Now, Mars is around a quarter the size of the Earth, so it's actually quite small when we talk about planets. It's smaller than the Earth, obviously, smaller than Venus, and only a little bit larger than Mercury, really. But why are we observing it, and why is it so bright at the moment? Because you may have noticed that you haven't seen it all year round, and you don't see it every year so bright. And this is because of a few things. So last month, Mars was in opposition. This happened back on the 13th of October, and this is essentially where Mars and the Sun are on opposite sides of the Earth. So as the Sun sets in the west, Mars is rising in the east, and is in the sky all night until it sets in the west, and then the Sun rises in the east. So the positioning means that all of the side of Mars facing towards the Earth is being illuminated with sunlight. So this is just like at full moon when we see the most of the moon, because all of that side of the moon is being lit up by the Sun. So the planets have phases in exactly the same way. It's just much harder to see those phases because the planets are so much further away. Now, you may have also seen Jupiter and Saturn over the summer and this evening too, but they're much further west at the moment. And that's because they were both back in opposition in the summer. You might remember seeing them appear really, really bright in the sky as soon as the Sun had set. So because they've moved away from opposition, they're not as bright now, but you can still see them really well. Now, the other thing is that Mars did come a bit closer to the Earth. So this evening, it's around 82 million kilometers away, but it made its closest approach to Earth on the 6th of October, when it was only 62 million kilometers away. So that's why it did appear a bit brighter a month ago compared to now, because it's moving slightly further away. Now, when we talk about the physical characteristics of Mars, I mentioned that, of course, Mars is the fourth planet from the Sun, so it's further away than the Earth, and that means its year is longer. A year on Mars is 687 days long, so almost twice as long as a year here on Earth. And it's tilted at 25 degrees, so it actually has distinct seasons like the Earth, but they're about twice as long. And so in the late summer, in the southern hemisphere, you're able to see features such as the ice cap. So if we have a look at a virtual simulation of Mars here, you can see in the bottom right there that there is a tiny little ice cap, and that's a southern ice cap. Because we're in late summer for the southern hemisphere, that ice cap has shrunk so it appears much smaller than in the winter months. And the image on the left here you can see is an image that we took last week of Mars. So because we've moved ahead 1 week, we won't actually see exactly the same features on Mars this evening as we saw a week ago. And that's because of the rotation of Mars. So it takes 24.6 hours to spin once on its axis, slightly longer than a day on Earth. So our view of Mars tonight, if we do see it, hopefully, it will be slightly shifted around. So we'll be able to see some different features, which is really quite exciting. It means that you can see something different weeks apart. So it's worth looking at Mars continuously. It's not just a one evening thing. You can keep looking at it for weeks to come. But let's just check back on our stream. Still nothing, unfortunately, with the cloudy weather, but this will be a good time to introduce you to the telescope that we're using. So I'm just going to hand over to Greg, who will talk to you about the telescope that he should be operating this evening.
Hi, I'm Dr. Greg Brown, one of the astronomers here at the Royal Observatory Greenwich, and I'm standing next to the device that we are using to observe Mars this evening, at least hopefully. This is the Annie Maunder Astrographic Telescope, and it is here in the Alt-Azimuth Pavilion at the Royal Observatory Greenwich. Now, it's quite a modern telescope. It was only installed 2 or 3 years ago, and it was designed to bring astrophotography and potentially even scientific research back to the observatory for the first time in almost 70 years. So very much to replace something that the observatory had a long time ago but has since lost, to bring that all back. And in order to do that, we have chosen a whole array of different telescopes attached to one single mount. So over here, behind here, we have the Takahashi telescope. This telescope is designed for deep sky observations, so things like nebulae and galaxies, very, very distant objects in our universe. At the bottom down here, we have a Lunt solar telescope. This one is designed to look at our own sun and not be affected by the fact that it's an extraordinarily bright object to try to look at. But the one that we're using today is the one in the middle here. This is the Celestron 14-inch telescope, or the C14. And this is a telescope which is designed for looking at relatively close by objects in the grand scheme of things, like the surface of the moon, or, for today, the surface of Mars and other planetary objects in our solar system. So this is a telescope which is 14 inches in diameter, and that means that it is far, far, far larger than your eye. Your eye is only about ½ centimetre across. That's the size of the opening that lets light into your eye. By being 14 inches across, this is the equivalent of an absolutely vast version of your eye, able to gather far more light in one go, and thus be able to see objects far, far fainter and in more detail than we can with our eyes alone. Now, this particular telescope is housed inside this building here, which is the Alt-Azimuth Pavilion, which previously had been somewhat empty. So it was brought into here to make use of a telescope dome that we had available, but weren't actually using at the time. And it's called the Alt-Azimuth Pavilion because it used to house a telescope that had a particular type of mount. Now, different telescopes have different ways of being mounted and being able to look across the sky. The telescope that we have here is what's called an equatorial telescope. It's a telescope which is aligned with the axis of the Earth's rotation. That means that when the sky is moving across our view, because the Earth is spinning, all you have to do is follow it in one direction. One single motor running at the same speed the whole time allows you to follow one object across the sky. Now, the telescope that was in here before was an Alt-Azimuth telescope, hence Alt-Azimuth Pavilion, and it was a telescope installed by William Christie, the 9th Astronomer Royal, who used this particular telescope to observe the moon specifically. Now, this particular telescope is called the Annie Maunder Astrographic Telescope, and that's because it's named after Annie Maunder, born Annie Russell, who was a solar observer and an avid astrophotographer. In fact, she was a pioneer in that particular field. And she's one of the forgotten women in astronomy that we really wanted to honour with this particular telescope, bringing astrophotography back to the observatory, as she was doing astrophotography all the way back at the turn of the 20th century here at the observatory as well. So this evening we're not going to be looking directly through the telescope with our own eyes. After all, then you wouldn't be able to see what we're seeing. But actually it turns out that most modern day astronomers at professional observatories don't use their own eyes to look through telescopes anyway. Instead, they use cameras, perhaps a little bit like this one, often in the bigger observatories out there, far bigger and far more advanced than even this. And these are designed to be able to provide either a live feed of what's going on through the telescope, which is what you're going to be seeing this evening, or potentially to build up a long exposure image of a faint object and see far more features on that object, or be able to see it in more detail than we can with just a live view. Another thing that we can do is that we can add filters onto our camera, a little bit like this one here, which we can use to enhance our observations in various different ways. Now, filters like this are designed to cut out certain colours of light. And you might think that would be a really bad idea. After all, we're looking at very, very faint objects. The last thing we want to do, surely, is cut out part of the light that we're seeing. But actually, there are very good reasons for cutting down the light to a very specific colour. So in this particular case, we are using a red filter. And that's simply because Mars, being a deep red object, many of its features are different shades of red. So by cutting out all of the colours of light that aren't red, we get a stronger contrast between darker and lighter regions on the surface of Mars. And that hopefully will allow us to see far more on the surface than we would be able to without our filter. Fingers crossed our observations tonight go well and we'll be able to see Mars in all of its glory. But I guess I'll have to find out later on.
So a big thank you to Greg there for telling us a bit about the Annie Maunder Astrographic Telescope. And we're back to our live observation, and unfortunately the weather has not yet improved, but still fingers crossed before we get to the end of our stream. But that's okay, we've still got more footage to show you. So these are some images that have been kindly sent to us in from the Flamsteed Society, who here at the Royal Observatory. And we've got some different close-up images and some images from further away where you can see just the redness of Mars when it looks more just like a star in the sky. But as Greg was talking to us about the history of our telescope, we thought it'd be important to tell you about the history of Mars observations themselves and why we've been doing it, really. So the modern telescope really gives us a very different picture of the planet than people had when telescopes were first invented. So Mars has been observed by humans for thousands of years. It's one of the classical planets that the ancients have known about forever. No one discovered Mars that we can really say. But the ancients knew that the planets were different from the stars. They moved in regular patterns, so they could watch them move across the sky, and they could tell because they look different. So if you look closely enough, you'll see that stars twinkle but planets do not. And this is because of the light that's coming through. So stars twinkle because they're a point light source. That light is going through the atmosphere and it's getting bounced around, but only in a single way. When we look at a planet, the planet doesn't twinkle because the light from the planet is being bounced around in different ways and enough that they cancel each other out by the time the light reaches your eye. So you'll notice, hopefully if you go out and look at Mars, that it won't twinkle, but the stars around it does. Now, Greg told us earlier a bit about the Annie Maunder Astrographic Telescope and where it got its name from. So Annie and Edward Maunder were astronomers who both worked here at the Royal Observatory Greenwich in the late 1800s to the early 1900s. Now, Annie's work was primarily solar research, so it's no wonder that AMAT has got that wonderful solar telescope on it. But it was actually her husband who conducted some experiments to investigate Mars. So to any of you who've read War of the Worlds, you'll probably be familiar with the idea of canals on Mars. So after the invention of the telescope in the 1600s, planetary observations became unsurprisingly much easier and far more fruitful. The late 19th century saw Mars absolutely catapulted into the public spotlight when Italian astronomer Giovanni Schiaparelli discovered canals on Mars. Now, American Percival Lowell took this a few steps further. He fine-tuned Schiaparelli's sketches with further observations, finally detailing a series of geometric waterway networks across the planet. He claimed these constructions could not have natural origins and therefore were man-made, or perhaps Martian-made. He went as far to explain that inhabitants around the equatorial regions of the planet needed water guided down from the polar ice caps to the exceedingly dry areas they lived in. Now, this was quite the claim. Astronomers around the world immediately turned their attention to Mars, some confirming Loeb's observations, whilst others remained sceptical, and Edward Maunder was one of those. He put forward immediate rejection and just thought that those claims were absolutely preposterous. So he set out to prove Lowell wrong, and he did just that, using nothing more than some paper discs and a group of children. So the experiment had the children draw what they saw on these paper discs from varying distances. Maunder showed that depending on the distance of the observer, individual features such as dots could appear as straight lines. It was therefore very possible that Lowell's canals were simply an optical illusion. His eyes were connecting small features like a planet-sized dot to dot. Now, it's also worth noting here that Percival was an amateur astronomer, and this became quite obvious when we take a closer look at his methods. Despite improved telescopes, changes in Earth's atmosphere caused blurring, so Lowell could only have a clear view of the planet for a fleeting second. He would then sketch his observation from memory, and these sketches, along with sketches from other astronomers, were then collated on a Mars globe. Lowell would then photograph the globe and then trace over the image to get his straight canals. Now, any of you familiar with the scientific method will know that that was just a pretty terrible way to conduct any sort of science. And people also thought it was quite surprising that the canals should have appeared curved because of course Mars is spherical and definitely not flat. So that was how Edward Maunder proved Lowell wrong, simply by getting children to draw what they saw on these different discs. But we can't be too hard on Percival. Because of his claim of canals, Mars became really, really popular. And the public, as well as scientists, really started to consider whether there was life on Mars or if there could be. Now, unfortunately, I still don't think we've quite got anything coming through our live feed, but we're going to take a break for a couple of moments, and then we'll come back and see if we can pick up any more of our images. So please bear with us and we'll be back shortly. Okay, thank you very much for bearing with us. So we've gone back to our live stream and still unfortunately the weather hasn't improved, but that's not to worry. We are still hopeful before the end of this stream. Now, I talked about the past observations of Mars, and you'd probably say really the observation that we've got here that we took last week isn't particularly clear. And unfortunately, this isn't really to do with the telescope itself. This is to do with the atmosphere. So there's something known as astronomical seeing, and this is what is causing the blurring and the wobbling of the image. And this will happen no matter really what ground-based telescope that you are using. It's the problem of having the atmosphere, and the only real way to improve our telescopic views in visible light is to send them out of the atmosphere. And that's where the Hubble Space Telescope really came in handy, because being out in space, having no atmosphere, that light doesn't get distorted. There are a few things that we can do here on Earth. Something known as adaptive optics can improve our feeds, but there really is a limitation due to the atmosphere, unfortunately. Now, we can see though that from our processed image on the left here, that we've got far more features. The image is a lot clearer. And so this is what happens when we take lots of images in quick succession and then we stack. AI is quite good at being able to stack images so that we can see features in more detail. We can see more defined edges. And here we can, of course, you can see the South Pole on our image, that lighter patch right at the bottom there. And then we've got these darker areas in the middle. And then the Northern Hemisphere that we know is smoother reflects more light. So that's why it appears a lot brighter, because it's smoother. Now, because of the limitations of telescope views from, of course, the Earth and then even out in space, we really need to go to Mars to be able to study it any further. And the first flyby of mission of Mars was back in 1965. The Mariner 4 space probe, which was a NASA mission, flew past Mars and definitely confirmed that none of those Martian canals were on the planet. And that's when we first saw more detail of Mars. It wasn't until 1975 that the first landers, Viking 1 and 2, landed on the planet. And then it wasn't until 1996 that Sojourner, the very first planetary rover, landed on Mars too, so was able to move around on the planet. So if you think just how far we've come in those few years, is really quite astounding. Then it was, of course, Opportunity and Spirit, which were two twin rovers in 2003. Unfortunately, both no longer operational. I think it was last year that we lost Opportunity. And Curiosity now is the one rover which is still functional on the red planet. And we're extremely lucky to have an interview to show you with Sanjeev Gupta from the Imperial College London. He's worked on the Curiosity rover for some time and is working also on one of NASA's future missions. So we interviewed him earlier in the week to find out a bit more about his work and really why it's worth exploring Mars in this way.
Okay, so hello, we're delighted to have Professor Sanjeev Gupta of Imperial College London, who is a planetary scientist who has been studying Mars for some time now. Sanjeev, thank you very much for being here.
Thanks, great to be here.
So why observe Mars in the first place? What makes it interesting, particularly for you?
So I'm actually an interloper. So I'm actually an Earth geologist, and most of my career has been actually working on modern environments on Earth. So I'm interested in surface processes, what shapes the landscape. I got interested in Mars accidentally, really. And what's fantastic about Mars is we have a really, really rich record of sedimentary rocks on Mars. In fact, we have an abundance of sedimentary rocks from really the earliest time of planet formation on Mars, way more than on Earth, because on Earth the oldest rocks have been destroyed by plate tectonic processes, so they're really deformed and horrible to look at, really, whereas they are pristine on Mars. And what's really exciting about those rocks is that they likely record a time that Mars was really warm and very wet, and so potentially habitable for life.
And that's a really interesting thing, that in some ways early Mars was somewhat similar to early Earth, is that right?
That's right. So the oldest evidence for life that we can be sure about is 3.5 billion years ago, and we have these things that are called stromatolites, which are they were sort of sticky mats created by microbes which sediment got trapped in. You can see these beautiful layers and domes, etc., and we can be certain that those are almost certainly formed by early life. But we have rocks on Mars of that age, and to me it seems surprising that life only arose on Earth and didn't arise on Mars. And so we can look for that evidence in those rocks on Mars.
So you've been involved for some time in the NASA Curiosity rover. In what way, how have you been using that mission to try to understand Mars?
So I have two roles on the mission. Firstly, I'm a scientist on the mission. I'm part of the MarsCam camera team. And my role as a sedimentologist and geologist is to basically pick targets for imaging the landscape and rock outcrops on Mars, where Curiosity is, and basically selecting targets and actually thinking about where we're going to drive, etc. And then interpreting those images in terms of what processes formed those rocks, what was a paleo environment, and what are the likely, was it habitable for life, basically. And then to lead to all these other questions, should we drill there, etc., to look for chemical signatures of life, etc. Secondly, I have a major operations role, so I'm one of 10 what we call long-term planners. And this is a strategic role where we work directly with project management in sort of guiding the science team to achieve its objectives, keeping them on the road, basically. And then I work with the engineers when I'm on shift, which might be 3 or 4 days a month, maybe longer, sometimes a week, where we lay out the plans for what the rover is going to do in the next few days to a week ahead. So most of the team basically work tactically. They turn up for shift on a particular day and they're just planning what the rover will do that day, what experiments we will do. But often those experiments have been strategically planned. And so that's my role, along with the other long-term planners, is thinking carefully about how we will achieve these goals.
So obviously for most of the history of astronomy, observing Mars has only been able to be done with a telescope from afar. What does Curiosity, what do rovers and landers get us that telescopes simply can't?
Well, we can take pictures that we can see images of rocks. If you look at the palm of my hand, you can see the lines on the palm of my hand. We can see things at that scale on Mars, and it's just completely changed the game of understanding the evolution of Mars. Very early in the mission, we were able to see images of pebbles encased in rock. And actually, that was interesting. Was we took a picture of a patch of light-colored rock with a navigation camera image, and we couldn't see the pebbles. And then we drove away. So we imaged the patch of rock with the MarsCam cameras, and then we drove away. When we got those images down, we could see these pebbles. Actually, when you walk around Greenwich here, you can actually find pebbles in the sediments. Here, the rounded pebbles were formed by rivers transporting gravels, basically, and they're too large to be moved by the wind. And so they were the smoking gun evidence, if you like, of water flow on Mars. Now, we knew, there's the old joke that NASA is always discovering evidence for water on Mars. And we've been able to see, channels on Mars, etc., for a long time with orbital images. But there's no other, with these rover images, there's no other way. And so many of our findings tell us completely new things about Mars. For example,
there are a number of other missions on their way to Mars at the moment, one which you're directly involved in, which is the Perseverance Rover. What will that be able to do that Curiosity couldn't, or perhaps do differently?
Okay, so Curiosity can do detailed chemical analysis, but scientists and geologists like myself really want samples to come back to Earth, where we can really analyze them in detail in Earth laboratories and look for chemical traces of life and biosignatures and all these other things. And so actually, Perseverance is the first step in this very exciting mission concept, which is called Mars Sample Return. And what Perseverance will do is going to a crater called Jezero, where we can see clear signatures of an ancient lake and a delta, and it will core and collect samples and cache them for future return to Earth. And then in probably around about 2026, 2027, there'll be another mission that lands on Mars, sends a fetch rover, which collects these samples, takes them back to the lander, and there's a Mars ascent vehicle that puts them into Mars orbit. And then a subsequent mission, maybe in the 2030, will collect them from Mars orbit and bring them back to Earth. And then we have another mission that the UK is playing a huge part in, which is the ExoMars Rosalind Franklin rover that was supposed to go again this year, but it's been delayed till with the launch date of 2022. Both Curiosity and Perseverance only drill to about 5 centimeters into the Mars surface. This is within the radiation damage zone, and the idea is that maybe the organics that are present will get destroyed.
Potentially signs of life, that sort of thing.
Etc. So what ExoMars, the Rosalind Franklin rover, will do is actually drill up to 2 meters into the rocks in the Martian surface and collect samples from below the radiation damage zone, and we'll analyze them. So that's not sample return, but we'll analyze the chemistry of these samples on the rover itself.
One last thing then. So there's been a lot of talk recently about the possibility of getting humans to Mars. How game-changing would that be when it comes to analysing the geology of Mars compared to rovers?
Yeah, it would completely change the game. I think what we might do in a week with the rover, we could probably do a couple of hours with a astronaut geologist, basically. And actually, we can do many more things. So the trouble is, obviously, with a rover, you're commanding it. There's latency. It takes time for us to analyze the data, etc. But also, a rover can't get everywhere. Whereas, obviously, a human is much more dexterous, but also can make cognitive decisions. So you can make decisions. Oh, look, this looks interesting. I'll go here. Oh, maybe that's not as interesting as what looks over there. And can make very rapid decisions and can map the terrain and move around in the terrains. And then if we do discover things, we'll actually want to discover more. It's not the end of the game. We don't say, oh, we found life, that's it, we'll move on to other things. No, we'll be absolutely sending lots of humans to astronauts to go and explore and discover. And the other important thing is that it's not just the life question, it's really that Mars has this very rich record of the early history of terrestrial planets that we don't have preserved on Earth. So actually, by going to Mars, we actually learn something about ourselves. And that's, to me, actually almost the most important reason.
Absolutely. Professor Sanjeev Gupta, thank you very much for joining us.
Thank you very much indeed.
And that was the fantastic Professor Sanjeev Gupta from Imperial College London, and the voice of our very own Dr. Greg Brown, who is in our AMAT telescope dome this evening. Unfortunately, our cloud here still hasn't shifted, but that's okay. We've had lots of questions come in from you, so I'm going to start answering some of those. But I would just like to say that Sanjeev's point about investigating Mars not only be about looking to discover things about the planet in itself, and about possibly alien life, but also how it helps us to really understand our own planet and where we came from, which is really just as important. Space isn't just about exploring outwardly, it's also about exploring ourselves too. So I thought that was a really good point. But I'm going to get to some of your questions. So we had from Zubi Warsi from YouTube asked how long it takes to get to Mars. sort of a question where it depends on a lot of things, but we'll go with our current measurements. So when we send a space probe to Mars, for example, the Perseverance mission, which launched back in July, that's due to land on the 18th of February. So some missions to Mars, if they're just taking spacecraft, which aren't that heavy compared to human missions, then we can get those there in about 7 to 8 months. So quite quick, really, to make an 80-odd million kilometre journey. That's pretty good going. But if we were to send humans to Mars, which hopefully we will, and possibly as early as the 2030s, then that we expect to take around 18 months instead. They're going to need a lot more equipment. The spacecraft's going to be much heavier, so it will take longer for them to get there. We have another question from Anam, age 9. How hot is Mars? A very good question, especially if we're going to send humans there in the future. So on average, Mars is actually minus 63 degrees Celsius. So pretty chilly, really. But in the equatorial regions, so where we get the most sunlight, in the summer, it can get up to around plus 20 degrees Celsius. So actually a lot warmer than it has been today here in the UK. Obviously the temperature changes throughout the year, but it is one of the planets where the temperature is roughly good enough for us to go there. Planets like Venus, for example, the temperature on the surface is plus 462 degrees Celsius. So we would definitely not want to send humans there anytime soon. And Anam also asked how you get to Mars. And the simple question to that is on a really big rocket. And if you've not seen any of the rocket launches, then I would really recommend, Anam, to have a look at some of the SpaceX rocket launches. So yesterday, the astronauts went to the International Space Station on a SpaceX rocket, and you can watch one of those. They always play them over on YouTube, so ask your parents to have a look at one of those. Okay. More questions. Oh, okay. Based on Andy Weir's The Martian, which is a very good book and a good film, the crew was hit by a big dust storm that nearly tips the rocket. Do such storms exist on Mars? So this is actually a really good point for observing Mars, because we don't just have to rely on our weather, we have to rely on Mars's weather too if we're going to see any features on the surface. So Mars has a really thin atmosphere. It's a carbon dioxide atmosphere, but it is really, really thin. So when we're looking at Mars, the features on the surface aren't really obscured. Occasionally we can see some clouds, and they do reflect a lot of light, so they'll look quite white. But overall, it is a good planet to look at. For example, Venus, which is a similar distance from us, it's got a really thick atmosphere. So we can't actually see the surface features through the atmosphere from here on Earth. So we're quite lucky with Mars. But it does have dust storms. So Mars is smaller than the Earth, and so it's got weaker gravity. It's got about 40% of the Earth's gravity, which is great for astronauts walking around. You could jump up and down about twice as high as you can here on Earth. But it also means that if dust gets kicked up, it gets carried around in the atmosphere really easily. So Mars is prone to global dust storms where the whole thing looks quite orange. You can't see any of the surface features, but it does have local dust storms continuously. It also has little dust devils, which is like a little whirlwind across the surface. And I've got another question of, can you walk on Mars? You definitely could walk on Mars. It would be easier than walking here on Earth because the gravity is weaker. But of course you would need a spacesuit. But more on that in a moment, because we have been asked if you need protective gear to walk on Mars, and you absolutely do. So first of all, the big one is that you're going to need a helmet and oxygen to breathe. The Martian atmosphere is mostly carbon dioxide, which humans can't breathe, so you need that for one. And secondly, you need to be protected from radiation. That very thin atmosphere means that damaging radiation from the sun can come straight through the atmosphere and potentially harm humans or any other living tissue. So you definitely need to wear protective gear to walk around on Mars. Now, a question about our telescope. Can a civilian own a telescope like AMAT? So hopefully you saw our video with Greg earlier and you saw our wonderful Annie Maunder Astrographic Telescope. So that's actually a combination of 4 telescopes together. The one that we've been using this evening is the C14, which is a Celestron 14-inch telescope to look at Mars, and that's really good for planetary or lunar observations. And a civilian can absolutely own one. It just depends how much you're willing to spend. You will definitely need a telescope dome, but there are lots of astronomy clubs and societies around that have their own, so they collaborate together and that you can use. So I'd really recommend having a look in the local area to the local astronomy club to see if they do have one, because they are scattered around the country for sure. Okay, a good question, very London specific here from Julia, about how can we see anything with the light pollution from Canary Wharf. So if you've never been to the observatory, then just opposite us across the river is Canary Wharf. Obviously lots of light coming from there. So the light pollution does affect observations, especially just with your eyes. If you've lived out in the countryside your whole life, when you look up you can probably see more stars than you can count. Whereas here in central London, you look up and you can really count most of them on 2 hands. But you can improve that. So with our AMAT dome that we have here, our telescope is focused on a small area and it's inside a dome, so that limits how much light is coming in. So we're only allowing the light from the object really that we're looking at to come in. So that's how we can see Mars, but we're lucky because it's very bright. We would be able to see much, much more if we didn't have all of this light pollution. So it is a bit of a shame, but it doesn't mean that observations have to stop or that we can't continue to do them. There's still lots of things worth seeing. But of course, if you can get out in the countryside to see more stars, then really, really do. Okay. We also have from Ralph in Greenwich, London. How can you see Mars? Where can you find it? So you'll be able to see Mars essentially as soon as the sun has set. It will be rising in the east as the sun setting in the west. But if you wait a few hours, it will be higher up in the sky. So right now would be a fantastic time to see Mars if the clouds weren't covering it, unfortunately. But you will be able to see it for months to come as well. It'll be moving further west as the time goes on. So from Greenwich, Ralph, if you want to be looking towards the observatory, not towards Canary Wharf, that might help you there, and it will be on your right. But hopefully you'll be able to see it soon. Okay, so we've got what are the heights of astronomical tech currently and what is being developed to improve the quality of telescopes on Earth and in space. So as I mentioned earlier, unfortunately with telescopes here on Earth we are really limited by the atmosphere. No matter how good a telescope we can build, the atmosphere will blur and warp that image. So that's why we send telescopes out into space, such as the Hubble Space Telescope, which doesn't have to deal with those atmospherics. A brand new space telescope, hoping to be launched, I believe now in 2022, is the James Webb Space Telescope, which has been due for a few years, and that is Hubble's successor. It will have some visible light capabilities, but mostly infrared. And that will enable us to see far more than Hubble has. It will be really exciting time in astronomy once the James Webb Telescope gets its first light. So fingers crossed for that one very, very soon. Yeah, it's far bigger than Hubble. I haven't got the numbers off the top of my head, but it will be an incredible telescope, and that's really the future of observational astronomy. Okay, what are the benefits of studying Mars in depth than Io or other moons and planets? So that's a great question. So Io is one of the 4 Galilean moons of Jupiter. So it's one of the 4 largest moons. And Io is really interesting because It's the most volcanically active thing in the whole solar system. It's got over 400 active volcanoes and it's constantly erupting. If you've ever seen a picture of Io, it's this yellowish colour, and that's because it's covered in sulfur dioxide, which gets spread across the moon when those volcanoes erupt. So it's a really interesting place tectonically to have all of that going on. So Io in itself is definitely worth exploring, but why Mars as opposed to Io or other places? So Mars, for one, it's much easier for us to get to than other places. So Io, for example, out by Jupiter, hundreds of millions of kilometers further away, very difficult to get to. Mars, 80 or so million kilometers, a bit easier for us, so it doesn't take as long. The other thing is that we have to think about communication. When we send robots, we need to communicate with them, and the communication happens at light speed. So if we're closer, we can hear things quicker. Otherwise, we have to wait time to send a message and wait for the message to get back. So it's much easier operationally as well once we're there to visit somewhere closer. As Sanjeev Gupta also mentioned in his interview about how studying Mars helps us understand our own planet. And that's really important. So Mars could have very much been like Earth. It's sort of preserved a really early Earth, how Earth could have been. And Mars never got that far to have the trees and possibly the life because it lost its magnetic field, it's much smaller, and it lost its heat as well. So studying Mars, really, really important, and this prospect for life. We know that Mars once had running water covered in oceans and rivers, so I think it's really important to study it, to look for life, really. But great question. There are definitely other moons and planets that I would love to go to, and there are many missions planned in the future. Okay. Oh, this is a good one. Why is Mars named Mars? So Mars is named after the Roman god of war. And no surprises as to why, because it is bright red, and red has always been associated with war and violence. So that's where that comes from. It's the Roman god of Mars, Roman god of war. So all of the planets are named after Roman gods except from Uranus. That's got a Greek name, but its Roman name is Caelus, which I prefer, to be honest with you. So maybe we can call it Caelus. Ooh, this is a good question from Mirza. Do you believe in aliens? I would say I personally believe that there must be life somewhere in the universe. Given how many billions of stars there are in our galaxy alone, there's somewhere between 200 and 400 billion stars. For every single star, we think there's at least one planet. So that's maybe 400 billion planets just in our galaxy, when there are hundreds of billions, if not trillions, of galaxies. So for me, I think the possibility of life could be there, but whether we'll find it or not, I don't know. I'd be very hopeful, I'd love to, but I don't know. Okay, gosh, so many questions. Unfortunately, we haven't got time to answer them all. As you can see in our live stream behind me there still is no picture. Unfortunately, this heavy cloud has not moved. But we'll just see one last time the footage that we should have seen of Mars here. So thank you very much for joining us on our live stream this evening. I hope you've enjoyed it. I'm very sorry we didn't get to see a live picture of Mars, but the footage that I was showing you was captured from our Annie Maunder Astrographic Telescope only last week. And we hope to get more images out to you guys soon. I want to say a big thank you to my colleagues over in the dome there, so Dr. Greg Brown and Bryony Lanigan, and a big thank you to the Royal Astronomical Society for inviting us to be part of National Astronomy Week with them. If you want to head over to our website, rmg.co.uk, you can check out more of our upcoming events. This Friday, we have an evening with astrophotography, which is a panel discussion about the IAAPY exhibition with judges from the competition and astrophotographers who submitted, so that will be a really good evening. And as well, when the museum reopens, after the lockdown ends, the IAAPY astrophotography gallery will be reopened too, so you can visit it then. So that's it from us. Thank you very much for joining us, and I hope to see you again.